In this lesson, we're going to discuss reaction mechanisms. So what is a reaction mechanism? It is a series of elementary steps that, when combined together, will describe a chemical reaction. Often in one elementary step, an intermediate will be formed, and then it will be reacted in a subsequent step so that it never appears in the overall reaction. Here is a chemical reaction that has a two-step proposed mechanism. Step 1, step 2. The blue spheres are nitrogens, the red spheres are oxygens, the black spheres are carbons. So you can see we've got NO2 and NO2 and NO3 and NO. And then NO3, CO, NO2, and CO2. So this mechanism has two elementary steps. Each step would have its own rate constant. So we'll call them rate constants 1 and 2. And in the first step, we make NO3. That's a product. But then in step 2, it's a reactant. So that's an intermediate. Okay, and we would cancel that out. If you take a look at what's left, we've got two NO2s on the reactant side, and then on the product side, we've got one NO. Let's make that a 2 there. And we could cancel out one of those, and everything that's left now appears in the overall balanced chemical equation. So the sum of the two steps is giving us the overall reaction. We need that for our mechanism. When we add the elementary steps together, we should get the overall balanced chemical equation. And the mechanism does have to agree with the rate law for the overall balanced chemical equation, although we're not looking at that right now. More mechanisms could be possible. And this mechanism can never absolutely be proven as a correct mechanism. So now let's talk about the difference between intermediates and catalysts. We have a three-step mechanism here, and the overall reaction is down here. You can see that NO2 is produced in step 1 and then is consumed in step 2. So that would be an intermediate. And then an oxygen atom is produced in step 2 and is consumed in step 3. That would also be an intermediate. So now, what about NO? It doesn't appear in the overall equation. NO would be a catalyst because it is not consumed in the reaction. So you start with it, and then it is still there at the end. NO would be a homogeneous catalyst because it is in the same phase as all of the reactants and products. The mechanism that we just looked at had 3 elementary steps. And an elementary step is a reaction whose rate law can be written from its molecularity. Molecularity is the number of species that must collide to produce a reaction. If we have a unimolecular step, we have one molecule, and that's first order. A bimolecular step has 2 species, that's second order. A termolecular step is very rare and involves the collision of 3 species. Now, the probability of 3 molecules colliding simultaneously is very small, and so that's why this is very rare. This table summarizes the elementary steps, the molecularity, and then the rate law that results. Notice for bimolecular, you have a couple of options. two of the same reactant or two different reactants. And the same thing applies for termomolecular, two reactants or three different reactants. Take a look at the rate laws for each of the different types of elementary steps. For unimolecular with one reactant, our rate law shows first order with respect to A. For bimolecular, our rate law is showing second order with respect to A when both reactants are A. For bimolecular that has two different reactants, the overall reaction order is also showing up as second order. Remember, first order with respect to A, first order with respect to B. The overall reaction order is 2. And then for termomolecular, when we have 2 of A and 1 of B, we've got second order with respect to A, first order with respect to B. That overall reaction order is third order, 2 plus 1. And when you have termomolecular with A, B, and C, first order with respect to A, to B, to C, the overall reaction order is third order, 1 plus 1 plus 1. The elementary steps in a mechanism all occur at different rates. So a reaction is only going to be as fast as its slowest step. We call it the rate determining step. That will determine the rate law and the molecularity of the overall reaction. This photo is an analogy for the rate determining step. The rate at which the blue liquid goes into the flask is determined by the size of the funnel, not by how quickly the person is pouring the liquid into the funnel. So if we are evaluating a reaction mechanism, it has to meet these two requirements. We have to have the sum of the elementary steps equal to the overall balanced chemical equation for the reaction, and the mechanism has to agree with the experimentally determined rate law. So that rate determining step, its rate law, has to match the overall rate law for the chemical reaction. Remember again, mechanisms can never be proven, but if they meet these two criteria, we can say that it is a plausible mechanism. So here you can see an overall reaction and its experimentally determined rate law. And then there's a mechanism here that has two elementary steps. We've got one intermediate, the fluorine atom that's produced in step 1 is a reactant in step 2. And then everything that's left is in the overall balanced chemical equation. We've got two NO2 molecules, a fluorine molecule, and then two of these NO2F molecules. So this mechanism does meet the criteria of when you add the steps together, you get the overall balanced chemical equation. The other criteria is to see if the rate determining step, its rate law, matches the overall rate law for the given reaction. So step 1 is the slow step, that's our rate determining step. And if we're going to write the rate law based on its molecularity, we get, this is two different reactants, so it is bimolecular. And this is how we write the rate law for a bimolecular step that has two different reactants. Now this rate law does match the overall rate law for the chemical reaction, so we have met the second criteria. Remember, other mechanisms for this overall reaction could be possible. And in a later lesson, we're going to discuss what happens if the rate determining step, the slow step, is not step 1.